This is a revision video for the Year 13 Inorganic Chemistry topic of Period 3 and their oxides. If you haven't already, I'd take a look at the Year 12 Period 3 video, but we'll do a brief recap here. Period 3 are the third row of the periodic table, and the 8 elements in this period all have 3 shells, so their electron configuration ends with either 3s or 3p. Here are diagrams of sodium, magnesium and aluminium, and as you can see from their relative sizes, the general trend is that as we go left to right across period 3, atomic radius decreases. This is partly because the number of protons is increasing by 1 each time, so there's a higher nuclear charge. This means that there's a stronger electrostatic attraction between that positive nucleus and the valence electrons in the outer shell, and therefore that outer shell comes in closer and closer to the nucleus. However, it's also important to mention that the atoms have the same number of shells, so there's no increase in shielding. The first ionisation energy of an element is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to make 1 mole of gaseous ions with a single positive charge. Again, the general trend is for this to increase as we move left to right across the period, but there are some exceptions. So firstly, we see this increase happening, and this is because there are more protons as we move left to right across the period, and therefore a stronger electrostatic force of attraction between that nucleus and the electrons. However, we see aluminium deviate from this trend, and the reason for this is that aluminium's outer shell electron is in the 3p subshell rather than the 3s subshell. It's higher energy and therefore it requires less energy to remove. Silicon and phosphorus then follow the general trend that we've been expecting. But when we get to sulfur, again we see a dip, and the reason for this is that for the first time we have 2 electrons sharing a 3p orbital. These electrons, like all of the rest of the electrons in the atom, are repelling each other, and this repulsion makes it easier to remove one. Then when we get to chlorine and argon, we're back to that general trend of it taking more energy each time due to the greater number of protons. The differences in melting points as we look at the period can be explained by their structure and bonding. Sodium, magnesium and aluminium have metallic bonding, and this requires a relatively large amount of energy to overcome, and so therefore these metallic elements have relatively high melting points. Magnesium and aluminium have higher melting points than sodium because they have more valence electrons and also a higher charge on the cations, and both of these contribute to a stronger electrostatic force of attraction. Silicon has a very high melting point indeed because it forms a giant covalent structure. Phosphorus, sulfur, chlorine and argon have comparatively low melting points because these are held together only by weak van der Waals forces. But we can explain the relative size of those 4 elements' melting points by thinking about the sizes of the particles. So of course we have P4, S8, Cl2 and argon is monatomic. So sulfur as the largest molecule has the highest melting point, followed by phosphorus, followed by chlorine, with argon being the lowest. The first part of the Year 13 content about Period 3 is about the reactions of sodium and magnesium with water, and of course sodium, or the alkali metals in general, reacting with water is pretty much everybody's favourite experiment from GCSE chemistry. So you hopefully remember that sodium reacts very vigorously with even cold water, and it makes 2 products. Sodium hydroxide is of course an alkali, and therefore it turns universal indicator blue, and also a large amount of hydrogen gas is released. And we can prove that that's hydrogen gas by igniting it and listening for that characteristic squeaky pop. In contrast to this, magnesium reacts very slowly with cold water. It will undergo that same process making magnesium hydroxide and hydrogen gas, but you're unlikely to see more than a few very small bubbles, and gradually over time watch a solution that's had universal indicator to it turning slightly blue. However, if you react magnesium with steam rather than cold water, then it reacts much more vigorously, and also it forms a different product. It makes magnesium oxide rather than magnesium hydroxide. Now this topic isn't just a rehash of Year 12, it's not just about the properties of Period 3, it's also about the properties of their oxides. So you need to know what those are, what the formulae for them are, and also how they form. As you know, sodium is extremely reactive, and it will react with oxygen even when it's cold, even when there's no further intervention. But if you do burn sodium in oxygen, then you should know from your Unit 8 triple chemistry from GCSE that it burns with a yellow flame, and it produces a white solid with the formula Na2O. Next comes magnesium oxide, and if your favourite part of lower school chemistry wasn't watching the alkali metals being put into water, then maybe it was burning some magnesium in a Bunsen burner flame. And hopefully you remember that this gives off a really bright white light that you were probably told not to look directly at. And at the end of the reaction, you're left with this white powdery substance, which is magnesium oxide. The next few elements also react in similar ways. So aluminium will react with oxygen under high temperature to produce a bright white light and aluminium oxide. And you see this white powdery substance as sort of almost like smoke. This is the same aluminium oxide that coats the outside of all things that are made of aluminium. So if you think about something like an aeroplane, it doesn't make sense to make it from aluminium because aluminium is super reactive. But the aluminium oxide on the outside of the aeroplane is very corrosion resistant, and therefore it protects the rest of the aluminium underneath from reacting with the oxygen in the atmosphere. Silicon also reacts with oxygen, releasing a bright white light, but only at extremely high temperatures, and often having to use something like magnesium as a fuse to start the reaction. And then phosphorus will also react with oxygen to release a bright white light and a white powdery substance. It's worth noting in particular what the formula of the phosphorus oxide is. Here, phosphorus has an oxidation state of 5, and that might lead you to think that it should be P2O5, but it's not, it's P4O10. And the reason for this is that this isn't an empirical formula, because phosphorus oxide isn't an ionic compound, it's molecular. So the P4O10 doesn't represent the simplest possible ratio between the elements, it represents the actual number of atoms in the molecule, and that's a really common mistake to make under pressure in the exams. Then we have sulfur, which can react with oxygen to either make sulfur dioxide or sulfur trioxide. In the summary at the start, we talked about how important structure and bonding were for explaining the melting points of the period 3 elements, and that's also true when we think about their oxides. Sodium oxide is of course ionic, and therefore it has a relatively high melting point because it takes a lot of energy to overcome that strong electrostatic force of attraction between the positive sodium ions and the negative oxide ions. Magnesium oxide is also ionic, but it has a higher melting point, and we can explain this by thinking about the relative charge of the cations. A magnesium 2+ ion is able to attract the oxide ion more, and therefore it requires more energy to overcome that strong electrostatic force of attraction. Now you might think of aluminium oxide as being ionic, but it does show some covalent character. This can be explained because of the electronegativity difference between the aluminium and the oxide being less big, or just because those small aluminium ions have high charge and therefore they're able to get close to the oxide ion and distort the oxide charge cloud. Silicon dioxide is a giant covalent structure and therefore it has a very high melting point. And then our final 3 are simple molecular structures with much lower melting points because it's only the weak van der Waals forces between the molecules that need to be overcome, not strong covalent bonds. The general rule of thumb is that when metallic oxides dissolve into solution, they form alkalis, whereas when non-metallic oxides dissolve, they form acids. In the middle, we've got aluminium oxide and silicon dioxide, and these are both basically insoluble and therefore don't affect the pH. To give a little bit more detail, sodium oxide and magnesium oxide are both able to act as Bronsted-Lowry bases, accepting protons or hydrogen ions in order to make hydroxides. Sodium hydroxide is more soluble than magnesium hydroxide due to a weaker strong electrostatic force of attraction between the two ions. Therefore, it dissolves more easily and therefore it releases more hydroxide ions, and this leads it to have a higher pH, although magnesium hydroxide is still alkaline. Aluminium oxide and silicon dioxide are insoluble, so they don't affect the pH, and phosphorus oxide and sulfur dioxide and sulfur trioxide can all dissolve to produce different acids. Phosphoric acid forms when 1 mole of phosphorus pentoxide reacts with 6 moles of water. This phosphoric acid can then dissociate in water to form dihydrogen phosphate ions. Sulfur dioxide can react with water to make sulfurous acid with the formula H2SO3, whereas sulfur trioxide can react with water to make the more familiar sulfuric acid. You also need to be able to explain, using symbol equations, how these acidic oxides react directly with bases, like this phosphorus pentoxide reacting with sodium hydroxide. Now these can be a little bit challenging to remember, and I personally find it helpful to imagine that you're dissolving it to make an acid first. So we know that 1 mole of phosphorus pentoxide will react with 6 moles of water to make 4 moles of phosphoric acid. Now it's just a basic acid-alkali reaction where 1 mole of hydrogen ions combines with 1 mole of hydroxide ions to make 1 mole of water. So my phosphoric acid reacts here and we make the salt and also the 12 moles of hydrogen ions and 12 moles of hydroxide ions, which can come together to be water. If we join this equation together with the previous equation, then we're left with something like this. And what you can see now is the 6 moles of water that I added at the start that aren't really supposed to be in the reaction are being balanced out by the 12 moles of water that I make. So we can just cancel those out and we're left with a final equation in which 1 mole of phosphorus pentoxide reacts with 12 moles of sodium hydroxide to make 4 moles of salt and also 6 moles of water. And we can also express this as an ionic equation that looks a bit like this. The equivalent equations for sulfur dioxide and sulfur trioxide are much more straightforward and easier to remember than the one for phosphorus pentoxide. 1 mole of either one of these gases reacts with 2 moles of sodium hydroxide to make 1 mole of salt and 1 mole of water. Sulfur dioxide forms sodium sulfite, or to give it its proper IUPAC name because AQA will, sodium sulfate 4, where the Roman numerals 4 represents the oxidation state of sulfur in the SO3 2- ion. And then sulfur trioxide forms sodium sulfate or sodium sulfate 6. Again, we can also write ionic equations for each of these in which we skip the sodium spectator ions. You first met silicon dioxide or silica as part of GCSE chemistry, where it was used as an example of a giant covalent structure or a macromolecule. So you already know that it contains thousands of atoms covalently bonded together, and this makes it very hard, gives it a very high melting point, makes it very unreactive, and also makes it basically completely insoluble. However, chemists love to classify things, and so we want to be able to call it either an acidic oxide or a basic oxide. Now, silicon dioxide won't react at all with water or dilute alkali, but it will react with very concentrated alkali, and therefore we do classify it as an acidic oxide. When 1 mole of silicon dioxide reacts with 2 moles of sodium hydroxide, it makes 1 mole of sodium silicate and 1 mole of water. Aluminium, as ever, is the complicated one. So aluminium oxide is amphoteric, and amphoteric means that it can act as either an acid or as a base, in the same way that an amino acid does. You can remember this by thinking about amph like amphibian, which is an animal that can live in water and on land. So it's that idea of being able to do one thing or the opposite. So you need to be able to write simple equations for aluminium oxide acting as both a base and as an acid. To give you an example of aluminium oxide acting as a base, here we have it reacting with hydrochloric acid to make a salt and to make water. And again, we can write this as an ionic equation if we omit the spectator ions, which in this instance are those chloride ions. So instead we can just have aluminium oxide reacting with hydrogen ions from whichever acid you've picked to give you aluminium ions and also water. But aluminium oxide can also act as an acid. So here we have aluminium oxide reacting with sodium hydroxide to make sodium aluminate. And this is the equation when you did your GCSE required practical with the testing for the ions, and there was one hydroxide ion test that you didn't have to write the equation for, well, this is that equation. And this is definitely one to write on a flashcard and memorise rather than trying to figure out under pressure in the exam. And again, we can write this one as an ionic equation if we miss out the sodium from the sodium hydroxide. Finally, your two basic oxides will both react with an acid in order to make salt and water. So for instance, sodium oxide will react with 2 moles of hydrochloric acid to make 2 moles of sodium chloride and 1 mole of water. Of course, there are lots of different acids we could use, in which case we would make a different salt. So it might be easier to represent this with the ionic equation, as you can see here. Likewise, magnesium oxide will react with sulfuric acid to make magnesium sulfate and water, but again, we could use any different acid to produce a different salt, so we can also represent this with the ionic equation as you see here. Thank you very much for watching, and I hope you found that a useful summary of this inorganic chemistry topic. If you did, or if there are other topics you'd like me to cover, then let me know in the comments below. And don't forget to like and subscribe for more A-level chemistry videos coming soon.